As our friendly feline moves away from the patrol officers chasing her, the pitch of the sirens she hears lowers due to the Doppler effect, maybe to the point that the sound is outside the range of a cat's hearing. This could be used in her defense in a court of law. Do you see why everyone, including cats, should take a course in physics? So what exactly is the Doppler effect? Let's give a statement of it. The Doppler effect is the phenomenon where the wave frequency will change as the wave source moves relative to the observer. So as the wave source moves towards the observer, the observer will detect an increase in wave frequency. Now remember what we said previously, if it's a sound wave, then they would experience an increase in the pitch of the sound, since pitch, that psychological sensation of sound, is directly related to the physical quantity we call frequency. And likewise, as the wave source moves away from the observer, for that case, the observer will detect a decrease in wave frequency. Examples of the Doppler effect, we'll look at a few in this video, but in the next slide, we'll consider the example of a train horn that moves relative to an observer. So here you're going to see a video clip of a train that is approaching the station. And you'll notice what happens as the train approaches the observer. What happens to the pitch of the sound wave frequency, as well as what happens to the frequency of that train horn as the train actually passes the observer and moves away. Let's take a look. So did you notice the change in pitch of the train horn as the train first approached the station and then passed the station? As the train was approaching the station, moving towards the observer, you could hear the pitch of that horn go up. It became higher. Whereas once the train passed the observer in the station, then you heard this characteristic lowering of the pitch. So we're going to take a look at another example of a Doppler effect in the next slide, where this time you will look at the Doppler effect in the form of a buzzer, that when whirled above my head will move both towards and away from a fixed microphone. So that fixed microphone is going to serve as the observer in this case. Again, you should notice that the frequency or pitch of the sound changes as the wave source, that is the buzzer, moves both towards and away from the observer, in the form of the microphone. Let's check it out. All right, so folks, what I'm going to do here is I'm going to illustrate the Doppler effect for you. And what I have here in this little box is a buzzer, and I'm going to activate it here. You're going to hear it has a certain pitch. And right now that pitch should be fairly constant because, if this behaves as a sound source, it is not moving towards or away from you. But what we're going to do is I'm going to set this in motion. I'm going to whirl it in a vertical circle above my head. So there's going to be times during that motion where this object, this buzzer, is actually moving towards you. That is where the source is moving towards the observer.
And then there will be other times where the sound source is moving away from the observer. And what you should notice is a change in pitch. Okay, that change in pitch we said is characteristic of the frequency change that happens whenever a sound source moves towards or away from an observer. This is what we call the Doppler effect. So let me demonstrate this.
And as another example, one I think everyone can relate to, think of a time when a police car or fire engine with siren blaring has approached you and subsequently passed you. Think about how the sound you hear changes in time. There should be two distinct ways in which the sound changes, which we'll consider in the next couple of slides. I'll be the first to admit that the Doppler effect is not so obvious here, but I wanted to include the simulation to highlight the difference between the change in frequency, which is characteristic of the Doppler effect, and the change in loudness, which is something else entirely. Okay, so you should notice that there are two distinct and separate phenomena occurring in the slide. As the siren approaches, the sound clearly gets louder. Okay, while the siren may create waves of constant energy, the sound wave intensity increases as the sound source gets closer to you. Okay, remember that we said in part 2, okay, that for spherical waves, there is an inverse relationship between wave amplitude and distance. So we would expect that as you get closer to the source of the sound, or really as the sound source gets closer to you, the amplitude, okay, and therefore loudness increases. But the change in volume has nothing to do with the Doppler effect. So like I say, that is the reason that I'm including the slide. I want you to see there's a distinct difference between, okay, the frequency change and the volume change. The Doppler effect has to do with the change in frequency only. Okay, and here, although it may have been hard to notice, as the siren approaches you, there was a slight increase, okay, in the frequency of the sound that you would hear. Okay, whereas when the siren passes you and is moving away from you, okay, there is a drop in the frequency and therefore pitch of the sound wave observed. So what exactly causes this change in frequency? Let's start by taking a look at a few simulations to help us understand. In each of these simulations, you will see a wave source as well as an observer of the waves. You'll note what happens to the waves themselves as the wave source moves relative to the observer. This simulation will help us understand the Doppler effect. Notice that we have a source of sound over here on the left-hand portion of the screen, like a car horn, for example, as well as an observer of the sound, like you, the person, for example, even though both are represented only by dots in the simulation. Let's see what happens when the source of sound is at rest. That is, has no velocity. Notice here that the velocity is set to 0 meters per second. So when we start the simulation, you'll notice that okay, waves are created and travel outwards from the source towards the observer. You'll notice that it takes a certain amount of time for the waves to actually reach the observer, suggesting that waves travel at a finite speed. Let me pause the simulation briefly. Each of these circles represents a wave crest. Remember that the distance between any two wave crests represent the wavelength. And you can see here that there's a certain amount of distance or certain wavelength, okay, for this particular sound wave when the source is at rest. Okay, also remember that the frequency is a measure of the number of waves passing a given point per unit time. So for example, if I start the simulation again, and if you, the observer, were to count how many waves cross your path per unit time, okay, let's say per second, you would have a measure of the wave frequency. So try to make a mental image of both the wavelength and the frequency for the case where the wave source is at rest. Let's now set the wave source in motion, okay, towards the observer. So I'm going to set the source with a velocity of, let's say, about 200 meters per second. Okay, let's now visually notice what happens to the wavelength and the frequency as that source moves towards the observer. I'm going to pause the simulation here, okay, and observe the wavelength. Do you notice how the wavelength has been shortened, okay, when the source is now in motion towards the observer? Okay, remember that there's an inverse relationship between wavelength and frequency. When I start the simulation again, you'll notice here that when the source moves towards the observer, it's catching up to the waves that it's emitted, okay, and you will notice, okay, that, okay, for the case where the source moves towards the observer, okay, many more waves pass the observer per unit time. That tells us that the frequency increases. If this is a sound wave, we can then say that as the frequency of the sound wave increases, so does the pitch of the wave that you would hear. So you're seeing the Doppler effect in action. Okay, let me rephrase. As the wave source moves towards the observer, the wavelength shortens and the frequency increases. And like we said, for a sound wave, you would hear an increase in the wave pitch. Now let's consider what happens when the wave source of sound moves away from the observer. Okay, so in this case, I'm going to set the wave source to have a negative velocity, let's say about negative 200 meters per second. Okay, so that the wave source is now moving in the opposite direction. Again, let's observe what happens to both the wavelength and frequency as this wave source moves away from the observer. I'm going to pause the simulation here. Okay, hopefully you can visually notice when you measure the wavelength, okay, notice how big the wavelength is now for the case where the source is moving away from the observer. Okay, and like we said before, as the wavelength increases, the frequency decreases. All right, when I restart the simulation, you can see that far fewer waves are now crossing the observer's path per unit time, suggesting a frequency decrease. Okay, so you can see, once again, the Doppler effect in action. That as the wave source moves away from the observer, okay, the wavelength increases and the wave frequency now decreases. So the simulation you see in this slide nicely illustrates the same phenomenon. The wave source is represented by the tweeting of the bird, okay, while the observer can be considered this rather large human ear, okay, that you see on your screen. Notice in the simulation that as the bird moves towards the ear, the wavelength shortens, thus causing an increase in frequency and therefore an increase in pitch observed by the ear. Okay, likewise, when the bird moves away from the ear, notice the increase in the wavelength of the sound wave, okay, which would cause a corresponding decrease in frequency and pitch of the sound wave observed. In this slide, we'll review what we learned in the previous simulations in the last two slides, so you can get something written down in your notes. So starting with a case where we have the wave source being at rest, and if the red dot in this diagram represents the source of sound, notice that the red dot is not moving, okay, relative to the two observers, okay, the observer on the right represented by an ear and the observer on the left. Also notice that, okay, regardless of the position of the observer, okay, the wavelength that that observer will measure for the sound wave will be the same in all cases. Okay, that when they take a look at the wavefront diagram, because that source of sound is at rest, any observer will measure the same wavelength. Okay. Let's now take a look at what happens when the sound source is in motion relative to the observers. And so we're going to start by taking a look at the ear on the right here, where the sound source is moving towards the observer. Okay, you'll notice in this case what happens to the wavelength. Notice that the wavelength decreases, okay, it gets smaller. Compare that to the case where the source is at rest. You'll see that these wave fronts, okay, the distance between them is smaller, which suggests the wavelength decreases. And we know this inverse relationship between wavelength and frequency. You can imagine that, okay, as the wavelength shortens, more of these waves will pass by the observer's ear in any given time. When we now look at the ear on the left, we can see now for this ear the wave source is moving away from the observer. And as you can see, for this case, the wavelength increases. And that increase in wavelength corresponds to a decrease in frequency. For the case of sound waves, then, you see that, okay, when the wave source moves away from the observer, the pitch decreases, whereas when the wave source moves towards the observer, for a sound wave, the pitch would increase.
So hopefully you see qualitatively, okay, why the frequency will change when the source is either moving towards or away from the observer. What we now want to look is we want to come up with a quantitative description of this frequency shift, okay, and we're looking at a case here where the source moves but the observer does not, so the observer is stationary. In a few slides, we'll also look at the case where the source is at rest, but the observer moves. Remember, when we defined the Doppler effect, we said it was a phenomenon whereby the frequency changes because of the relative motion, okay, between the source of the waves and the observer. So we really have both possibilities. The source can move, or the observer can move, or both can move at the same time. So let's start by considering a stationary source. That's what I'm showing you in this picture here. So the little red circle, it represents our oscillator, which is emitting waves. Notice the source is at rest. So what we can say is that these spherical waves travel outwards at a constant speed. So right at the initial time, this crest right here, well, I'm not showing you the entire crest, but this represents a wave crest that is emitted, okay, right at the start of the problem. I'll say T naught. Okay, this crest right here, this is a crest that has been emitted, okay, one period later. Remember, the distance between any two wave crests is the wavelength. The time between any two wave crests is the period of the wave. So, okay, you can see the wavelength, okay, described in the diagram here. Now, the distance between any two wave crests is a wavelength. I'm showing you that in the diagram. We said the time between wave crest emissions is what we call the period. Okay, now the distance the wave crest travels in a time equal to 1 period is what we call the wavelength. Okay, and remember this wave crest that I'm showing you here, okay, had to travel a distance equal to the wavelength in a time equal to the period. It travels that distance at a certain speed. What is that speed? It's the speed of the wave in the medium. So we can say the distance the wave crest travels in a time equal to 1 period, okay, is equal to v, which is the speed of the wave in the medium times time, right? Distance equals speed times time. So what we now want to look at is, okay, that's when the source is at rest. What happens when the source is now moving to the right? Okay, for the source that is moving towards the observer, okay, what can we say there? So here you see our source, this is now moving at a speed v sub s. Be careful, okay? The speed of the source and the speed of the wave are two very different speeds. Okay, so you see that as the source moves to the right, okay, and it emits a new wavefront, okay, you can see that that new wavefront is a little bit closer to the wavefront that was emitted 1 period before that. Okay, because the source is in motion, it is catching up to the wave that is just emitted. So this is what we'll call lambda prime. This is the new wavelength, okay, because of the motion of the source, as opposed to our original wavelength where the source is at rest. So we want to come up with an expression for lambda prime. So the distance the wave crest travels in a time equal to 1 period, okay, like we said, is simply the speed of the wave times the period. Okay, but now we've got to look at the distance the source travels. Okay, that's really this distance right here. Okay, notice that when the source was at rest, okay, here it is. But because the source is moving to the right, after 1 period, it is now a distance here, okay, equal to the source speed times the period. That's what this distance is. So we can say that the source travels a distance v sub s for speed of the source times a period, okay, in a time equal to 1 period. You can now see that this new wavelength, lambda prime, is really equal to the original wavelength lambda minus the distance that the source has traveled in that time, right? So the new wavelength, the smaller wavelength, the reduced wavelength, is equal to the original wavelength minus the distance that the source has moved, okay, between those wave crest emissions. So we can write here, just making the substitution. Remember, lambda, we said, was just equal to the wave speed times the period, so we'll plug that in right here. Okay, and once we have this expression for our new wavelength, we can get an expression for our new Doppler frequency f prime. So from our wave equation, the speed of the wave is constant in the medium v, okay, but the wavelength and the frequency change. That's why we represent them as lambda prime and f prime. Solving for f prime equals v over lambda prime, and we will substitute in our expression for lambda prime. Okay, here vt minus v sub st, okay, which you see in our denominator down here. We'll factor out the period and recall that 1 over the period, the reciprocal of the period, is just the frequency. So at the end of the day, this is a quantitative expression for the frequency shift that occurs when the source is moving towards the observer. Notice that there are two speeds here. V represents the speed of the wave in the medium. V sub s represents the speed of the source in the medium. Notice that if V sub s is 0, that is if the source is at rest, okay, then you find out that f prime is exactly equal to f, right? If the source is not moving, we just get vf over v, or just f.
We now have an expression for the Doppler frequency when the wave source moves towards a stationary observer. Let's now take a look at the case where the wave source moves away from the observer. So starting with the diagram you see on the right here on your screen, okay, you can see that when the wave source moves towards the observer, okay, what I'm showing you over here with the laser pointer, you see that the wavelength shortens by an amount, okay, that is equal to the distance the source moves in one period. Remember that, okay, as the source moves towards the observer, it's catching up with the waves that it's just emitted, okay, shortening the wavelength by an amount equal to the distance that the source travels, okay, in creating that wavelength. In other words, the distance the source travels in one period. Okay, when we come over here, however, and look at the left-hand portion of the picture, we see that the wave source is moving away from the observer, okay, and we can say for this case, the wavelength increases by an amount equal to the distance that the source moves in one period. So we can express this relationship mathematically, okay, as follows here. Okay, for the source moving away from the observer, okay, we can say that the new wavelength, lambda prime, is equal to the original wavelength lambda, okay, plus, okay, the speed of the source times a period. Okay, remember that the distance the source moves in one period is simply, okay, the speed that the source travels, okay, times the time, right? Distance equals rate times time. And the original wavelength, okay, coming from the wave equation, is equal to the speed of the wave in the medium, okay, times the time of travel, which is one period, which is the time required to make one complete wavelength. So if we want to now talk about the new frequency, okay, we simply use the wave equation. Okay, the wave speed in the medium equals the new wavelength times the new frequency. And making our substitution here, first solving the equation for frequency here. Okay, we will make the substitution here for lambda prime. Okay, so in the denominator here, we're going to substitute this expression here. And we would like to write this in terms of frequency, the original frequency, rather than the original period. Okay, so we can factor out the period from both of those terms in the denominator, and remember that 1 over the period is simply the frequency. So here we have an expression for the new frequency, the Doppler frequency, okay, that the observer would observe when the wave source is moving away from the observer. Thus far, we've considered the case where the observer was at rest, but where the wave source moved either towards the observer or away from the observer. And we've derived an expression for this changed frequency. Okay, that is the Doppler frequency. Okay, we're now going to consider a different case. Okay, the case where the wave source is now at rest, okay, but the observer is now in motion. We'll soon find out that this new scenario also results in a Doppler shift to the observed wave frequency, but for a very different reason. So let's compare and contrast these two situations, okay, in the following matrix here. So starting with the case that we're familiar with, okay, the one we've talked about already, where we have a moving source and a stationary observer. Okay, what we said previously is that the wavelength changes, okay, as the wave source moves relative to the observer. Okay, as the wave source moves towards the observer, it's catching up with the waves it's emitted. Okay, and therefore that causes the wavelength to shorten. Okay, likewise, when the wave source is moving away from the observer, okay, that is going to make the corresponding wavelength increase. So clearly, for a moving source and stationary observer, the wavelength changes. But okay, the wave speed in the medium relative to the observer does not change at all. Okay, it remains constant, in which case the wave equation takes on the following form. Okay, we can say that the wave speed in the medium, okay, is equal to this new wavelength, the changed wavelength, which gives rise to a changed frequency. Okay, let's now take a look at this other scenario that we have not yet talked about. Okay, in this case where we have a stationary source, okay, but a moving observer. So as you see in the diagram here, this comes from the infamous comic strip Calvin and Hobbes. Okay, you can see in this case Calvin's father is screaming at him. He is at rest, so his voice represents the source of the sound, whereas the observer, Calvin, is actually now in motion towards the source. Okay, so in this scenario, you can see here in the wavefront diagram that the wavelength does not change, okay, due to the observer's motion. Because the source is at rest, okay, the wavelength remains constant. But what is different, okay, what does change is the wave speed, okay, relative to the observer. As Calvin is in motion, as the observer is in motion towards the source, okay, then the speed of the wave relative to him is going to increase. Okay, and likewise, in a situation I'm not actually illustrating in the diagram, if he was to move away from the source of sound, okay, then the wave speed relative to him, okay, would decrease. So this gives rise to a changed frequency, but like we said, for a very different reason. So here, when we look at our wave equation, okay, we see that the wave speed, okay, in the medium changes, okay, relative to the observer. So, okay, v is no longer constant, but you see here, so v prime equals lambda, the wavelength remains constant, but because the wave speed relative to the observer changes, this too gives rise to a change in frequency, okay, a Doppler frequency shift. Let's continue where we left off in the previous slide and derive an expression for the Doppler frequency when the wave source is at rest, okay, but now where the observer is in motion relative to the source. And we'll start with a case where the observer is actually moving towards the stationary source. So here, as you can see in the diagram, if the source of the wave is Calvin's father, okay, a sound wave that he is creating and he is at rest, okay, but now the observer, Calvin, is moving towards the source, the wave speed that Calvin will measure will be equal to the speed of the wave in the medium plus, okay, the observer's speed. So think about what you know about relative velocity from your course in mechanics. If you're measuring the speed of a car and you're at rest relative to the car, okay, then you would measure the car's speed v. If you're now moving towards the car, okay, the speed of the car relative to you will be increased by an amount equal to your speed. So if we think of the sound wave here as nothing more than an object like a car, hopefully this new wave speed relative to the observer should make sense to you. Now, I want to be really clear here that there's two speeds we're talking about, and we do not want to confuse them. V naught represents the speed of the observer, whereas V represents the speed of the wave in the medium. So, to get this new frequency, this Doppler frequency, we are going to use the wave equation. And you recall in the previous slide, we said that, okay, the new frequency, f prime, okay, happens not because there's a change in wavelength, the wavelength stays constant, but because there is a change in the wave speed as measured by the observer. So plugging in this expression here for the new wave speed, okay, relative to the observer, plugging that into the numerator here, okay, our wave equation takes this form. We can use the wave equation again to write the wavelength in terms of speeds and frequencies. Okay, so since the wavelength is constant, we can say that the wave speed in the medium, okay, is equal to the wavelength times the frequency. In which case, when we solve for wavelength, we find that the wavelength is the wave speed divided by the frequency. Okay, when we now make that substitution in for the wavelength here, okay, and do a little bit of algebra here, okay, we end up with an expression for the Doppler frequency that looks like this. So in this slide, we will quickly derive the other case, which is where the observer is moving away from the stationary source. And so in that case, we would say that the speed of the waves that the observer would measure, V prime, would be equal to the wave speed in the medium minus the observer speed. Okay, once again, V naught being the speed of the observer, V representing the speed of the waves in the medium. And according to our wave equation, we can say that the new frequency f prime is equal to v prime divided by lambda, where we substitute, okay, the v minus v naught in for v prime. Once again, we will say that lambda, we will express it in terms of speed and frequency. Okay, we can say that the wavelength lambda, which is constant, okay, because the source is at rest, is simply the wave speed in the medium divided by, okay, the wave frequency, not the Doppler frequency, but the wave frequency. Okay, when we look at a source, an observer at rest, okay, we can then make the substitution as we did on the previous slide here in for lambda. Okay, right over here we will substitute in, okay, V over F, and that will bring us to an expression for the new Doppler frequency, which looks like this. So in the previous 5 slides, we've derived 4 equations that can be used to calculate the Doppler frequency, okay, the change in frequency that results when either the source of sound is in motion relative to the observer, or the observer is in motion relative to the source of sound, or both. Okay, it is possible that both the source of the sound and the observer of the sound can both be in motion at the same time. And this equation that I'm going to put on the screen here, okay, will take all cases into account, assuming you know how to use it, of course. So here we see really that there's these 2 sets of signs, right, the plus minus, where we would say that the upper signs apply if the source and or observer are moving towards each other, okay, whereas the lower signs apply if the source and or observer are moving away from each other. But here's the plug I'm going to make here, okay, to you. I want you to think about this, okay. Instead of memorizing the signs for a given scenario, all you need to do is to ask yourself whether the situation in question, okay, whether the problem you're confronted with will cause an increase or decrease in frequency, okay, for both the source and the observer. Once you've identified this, then you can choose the signs that will allow for this required either increase or decrease in frequency. So let's take a look at, okay, what I'm talking about here. So if we look at this equation here, okay, when we look at the numerator here, we see we've got, okay, the two terms v plus or minus v naught. Now, in pretty much all of your problems, v, the speed of the wave in the medium, that's going to be given. That's not going to be an issue. You know, if you're talking about the speed of sound in a medium, it's going to be given to you. It's somewhere around 343 meters per second, but that can change slightly with temperature. Okay. Over here, though, we've got the speed of the observer, okay, in the numerator. So here you can reason and say, well, if the observer is moving towards the wave source, we would expect an increase in frequency. Therefore, we would choose the plus sign. If the observer was moving away from the source, we would expect that to result in a decrease in frequency. So we would want to make the numerator smaller, in which case we would choose the minus sign. Okay, so, you know, yeah, this involves a little bit of thought, but okay, it's not rocket science here. If we come over here and take a look at the denominator deals with the source of the sound here. So if the source is in motion, okay, well, we know that if the source is moving towards the observer, we would expect an increase in frequency. Okay, how do we get that? Well, because this is in the denominator, we would need to use the top sign here, the minus sign, to make the denominator smaller. Okay, making the denominator smaller will make the frequency bigger. So as I said, if the source of sound is moving towards the observer, we'll choose the minus sign to make the denominator smaller and frequency bigger. Whereas if the source of sound is moving away from the observer, we would use the bottom sign, the plus sign, to make the denominator bigger and the Doppler frequency smaller. So in the next several slides, we'll take a look at various examples to include or to get some practice with all of these different possibilities and how to use the equation.
All right, so let's take a look at this first of 4 sample problems. In this problem, we're told that as an ambulance travels east down Briggsmore at a speed of 30 meters per second, its siren emits sound at a frequency of 400 hertz. So it is always a good idea to draw a diagram showing, okay, if you have all of these possibilities, showing the source of sound and its velocity vector, okay, as well as the observer in the problem. And if the observer is in motion, you want to show the velocity vector for the observer as well. So do that for any problem, okay, to set it up. We're then asked in, okay, part 1 of the problem, what frequency is heard by a person in a car traveling west? Okay, notice we have a car traveling west, ambulance traveling east. Car is traveling west at 25 meters per second as the car approaches the ambulance. Okay, so like I said in the previous slide, this is the approach you want to take. You want to ask yourself, does the motion of the observer cause a frequency increase? Does the motion of the source of the sound cause a frequency increase or decrease? Okay, then you'll know which signs to apply. Note here that if we look at the source of the sound is moving towards the observer. That should cause a frequency increase. Notice when we look at the observer is moving towards the wave source. That too should cause a frequency increase. So here we're going to use, okay, the upper signs here. So notice that it's the speed of the observer in the numerator, and we said that the motion of the observer, okay, the motion of the car towards the source of sound would cause an increase in frequency, so we're going to use a plus here. And we said that the source of sound, which that expression is in the denominator, the source of sound is moving towards the observer. That too should cause the frequency increase. So we're going to make the denominator smaller and use the minus sign. So once you figure that out, the rest is just plug and chug. Okay, and we have to make sure that we've got the numbers right. So remember, V, that is the speed of the wave in the medium, which for the sound wave in air at room temperature is about 343 meters per second. The V sub O, that is the speed of the observer. Okay, that's the guy in the car over here traveling at 25 meters per second. And notice that these are speeds, not velocities. Okay, the source of the sound is the siren on the ambulance, and that siren is moving at 30 meters per second. So we plug in those numbers. The original frequency of that siren, okay, as it is being emitted, is 400 hertz. The only difficult part here is choosing the correct sign. So we did that. Okay, we choose the signs that make the frequency increase for both sound source and sound observer, and when we do the number crunching, we get this value of 470 hertz. Always check. Okay, the original frequency of the siren is 400 hertz, so yeah, we would expect that as the observer is moving towards that source of sound that it should be a higher frequency, which it is. All right, so in part 2 of the problem, okay, notice that we still have our ambulance traveling 30 meters per second in an easterly direction, emitting a sound from the siren at a frequency of 400 hertz. But in part 2, we're asked what frequency is heard by the person in the car traveling at 25 meters per second as the car moves away from the ambulance. So basically, this is what happened in problem 1, but now the car is past the ambulance. Our approach is going to be exactly the same. Let's ask ourselves, does the motion of the source of sound cause a frequency increase? Does the motion of the observer of the sound cause a frequency increase or decrease? So here we can reason that the source of the sound is moving away from the observer. That should cause a frequency decrease. And in this case, the observer of the sound is moving away from the source. That also should cause a frequency decrease. So we have really a frequency decrease, okay, for both of these motions. So to do that, and I just want to point out here that when I look at this expression, it's the observer speed on top. So I'm asking myself, okay, in the numerator, does the motion of the observer, okay, as the car relative to the source cause the frequency to go up or down? So here the observer is moving away from the sound. That should cause a frequency to go down. Okay, so I'm going to choose a lower sign. In the denominator, this is where we deal with the speed of the source. So I look at the source and I say, the source of the sound is moving away from the observer. That too should cause a frequency to go down. To make the frequency go down, I need to choose the plus sign in the denominator to make the denominator bigger. Once I've identified the two signs, the rest is very straightforward. I plug in the speed of sound, the speed of the observer, the speed of the source, and the original frequency, do the number crunching, okay, try not to make a mistake, and here we have the Doppler frequency of 341 hertz. Notice that if the original frequency of the sound is 400 hertz, okay, as that car passes the ambulance, it will measure a frequency of 341 hertz, which is clearly less. Okay, so here we see a decrease in the frequency due to the Doppler effect. All right, so in part 3 of the problem, okay, same ambulance, okay, that we had in parts 1 and 2, but in this case, we're asked to find what frequency is heard by a person in a car that's traveling 40 meters per second as the car approaches the ambulance. So you'll notice here that the car is moving faster than the ambulance, so it is actually going to be approaching the ambulance, moving towards it. So that is going to dictate that we choose a certain signs, okay, for our expression here. And here we will note that the observer is moving towards the emitted waves. Okay, that should cause a frequency increase, but that the source of the waves, that is a siren, is moving away from the observer. So for the speed of the source, okay, we need to make sure that the frequency decreases. So when we look at our expression here, this tells us what signs we're going to choose. Like we said, okay, the observer here is in the car, is moving towards the source of the sound, so the motion of the observer, okay, towards the sound source should cause an increase in frequency. We will choose the upper sign. But we look at the source of the sound, the ambulance is moving away from the observer, okay, so the motion of the source of sound should cause the frequency to go down. So here we have these two contradictory effects. And in order to make the frequency go down, we want to make the denominator bigger. We will choose the plus sign in the denominator. Once again, that's the hard part of this problem. The rest is just plugging in numbers. So we'll plug in, speed of sound, speed of the observer, speed of the source of sound, the frequency of the source of sound. Do the number crunching here, and you will find out we get a frequency of 411 hertz. So you'll notice here that it is slightly bigger than the original frequency of the siren. And here you can see that one of the effects, okay, that is the motion of the observer, causes a frequency to go up. But the motion of the source causes a frequency to go down. It looks like overall the observer's motion is the more important one, because overall it has it causes the frequency overall to go up very slightly. All right, so in this fourth part of the example, we still have the same ambulance traveling east at 30 meters per second with its siren blaring at 400 hertz. Okay, but in this follow-up problem to problem 3, we're now asked to find the frequency, okay, heard by a person in the car after the car passes the ambulance that it was approaching. So once again, okay, we ask ourselves, how does the motion of the source of sound and the observer of the sound, how would each of their motions cause the frequency to change in the problem? And here we can say that, okay, the observer in the car, okay, moves away from the source of sound, okay, so that should cause the frequency to go down, but okay, the source of the sound, the siren, is moving towards the observer, so that motion should make the frequency increase. So once again, we have these two somewhat canceling effects. And when we look at our expression here, okay, for this Doppler frequency here, once again, the observer, the speed of the observer is in the numerator, and we said that the observer is moving away from the sound source. We should expect a frequency decrease, so we will choose the negative sign to make the numerator smaller. And once again, when we look at the source of sound, the source of the sound is moving towards the observer. Okay, the source of sound is in the denominator. Sound source moves towards the observer. That makes the frequency go up. So we would want to choose the upper sign, the negative sign here, to make the denominator smaller. So with those choices, okay, the rest is very straightforward. So we're going to choose the negative sign in the numerator, negative sign in the denominator, plug in the other numbers, and you'll notice here that we end up with a Doppler frequency of 387 hertz, which is actually less than the original frequency. So these two opposing factors, you can see here, okay, that the motion of the observer away from the sound wave had the bigger effect. okay, was more significant in causing that frequency decrease than the motion of the sound source towards the observer was in causing the frequency to go up. So look, folks, I just want to say here that when you are solving these problems, it is important that you get these signs right. And I'll be honest, I'm not going to give credit if you get the signs wrong in the problem, because I don't think that, if you to understand the physics means you have to understand how to choose the correct signs to make the frequency change, okay, according to the motion of both source and observer. So tell yourself that, okay, that you can plug in all the numbers, but if you get those signs wrong, you're going to get very little credit, okay, in your solution. All right, so in the examples we've looked at thus far, we have talked about the Doppler effect for sound waves. But like we said, the Doppler effect is a wave phenomenon and applies to all waves. So let's take a look at a couple of important examples of how the Doppler effect is used with electromagnetic radiation, okay, with light. So qualitatively, we'll take a look at how weather forecasting uses radar. And you may have heard on one of our local radio stations, KCRA3, they always talk about live Doppler radar. Okay, and this live Doppler radar is used to not only locate a storm, but to determine the speed of a storm as well. So let's take a look. If you take your transmitter here and you send a source of radar waves, and we will learn later that these are electromagnetic waves in a fairly low frequency. They're in a frequency of the electromagnetic spectrum that is below, okay, the frequency of visible light, so in the radar region of the spectrum. So when you shoot these low frequency light waves, electromagnetic waves at the storm, okay, the waves are sent and are reflected off the storm, and just like the way a motion detector works in our lab, the amount of time it takes between sending the waves, okay, between transmitting the waves and receiving the waves is detected, and knowing the speed of the waves, you can then figure out the distance of the storm, okay, or the location of the storm in relation to the radar, okay, transmitter. So the first thing that the transmitter does is to figure out how far away the storm is. The Doppler effect has not been used yet, but now, okay, the frequency shift of the reflected radiation is detected by the detector, and from that new frequency, okay, the computer can go through the calculation that we looked at on the previous slide. If this storm is now moving either towards, okay, the source of the waves, that is the radar transmitter, or away from the radar transmitter, okay, we can then use that equation to determine the speed of the storm. Okay, as long as all those other quantities are known, you can then use the equation. As long as you know the original frequency and the new Doppler frequency and the speed of the waves in the medium, you can then find the speed of, okay, the let's say the observer here, okay, the storm, as well. Perhaps even more importantly, the Doppler effect was used by astronomers to discover something very important about our universe, okay, and that is the motion of our galaxies. This is one of the biggest discoveries in astronomy, okay, in the last century. So astronomers discovered that light we see from distant galaxies is shifted towards the red end of the electromagnetic spectrum. Now in this visualization here, you can kind of see, okay, that If we have a source of light, like let's say a star that is moving away from us, if we're over here to the left, look what happens. Okay, that light gets shifted to the red end of the spectrum. If you're observing a source of the waves, let's say a distant galaxy moving away from you. If you were over here on the other side and that galaxy is coming towards you, okay, you would expect to see light shifted to the blue end of the spectrum. Okay, and just making that observation is very important. And we'll quickly go through this qualitatively here. So which color of light, red or blue, has a longest wavelength? Well, it turns out that red light has a longer wavelength than blue light. How does the frequency of red light compare to the frequency of blue light? Well, you know this inverse relationship between wavelength and frequency. Okay, so basically longer wavelength, lower frequency. That means the frequency of red light is less than the frequency of blue light. So here's the crux. In thinking about these answers, along with the Doppler effect, what can you conclude about the movement of distant galaxies? If we see the light from distant galaxies shifted to the red end of the electromagnetic spectrum, that would suggest that distant galaxies are moving away from us. That is, the source of the light waves, those distant galaxies, have to be moving away from us, the observer, to cause the shift towards the red end of the spectrum. And okay, we can look at that with one more visual here. Okay, you'll see here it's pretty much the same idea, but if you're an observer over here and the galaxy is moving away from you, you're going to see red light when you look through your telescope. If you were an observer over here and you see this galaxy moving towards you, okay, you will see a shift in blue light when you look in your telescope. So the last topic that we will introduce in this unit on sound is that of shock waves and sonic booms. In this slide, we will review, okay, some of the physics that we learned for sound sources, okay, when they rest and when they are moving relative to an observer. So a lot of this will serve as a review. When the source of the sound is zero, okay, when the source is at rest, okay, then the sound source sends out a spherical wave where the wavelength will be constant, okay, regardless of the observer, okay, regardless of where the observer is located looking at this wave. This is the case where the source of the sound is not moving. And we said when the source of the sound is moving, now we expect to see a Doppler effect, okay, a Doppler shift in frequency. Let's look at the case where the source of sound is greater than zero. In other words, the sound source is not stationary, but where the source of the sound is moving at a speed that is less than the speed of sound in the medium. And this is what we looked at. So in this case here, we see the sound source is moving to the right, and if you're in the region to the right, so you see that sound source moving towards you, you see an increase in frequency of sound, whereas if you're in this region over here to the left of the sound source and you see the source moving away from you, you would see the characteristic Doppler decrease in frequency, okay, of the sound wave. What would happen, however, if the source that is emitting the sound wave, okay, we're traveling so fast that it were actually traveling exactly at the speed of sound itself? Well, imagine what that wavefront diagram would look like. Okay, it would look like this. The source of sound emits a wave, okay, and that wave is traveling at a speed, the speed of sound in the medium, but so is the source of sound. It's also traveling at the same speed. So you see here how the sound source, okay, is always, okay, right, it is always right at the wavefront that it has just emitted. All right, so now we look at the case where we get the sonic boom. What happens when the source of sound exceeds the speed of sound? That means the sound source is traveling faster than the speed of sound. Well, if you take a look at that wavefront diagram, okay, you can imagine what would happen when the source of sound actually outruns the wave speed, the waves it's creating. And you see here, you get this conical shock wave where you get a whole lot of overlapping wavefronts. And it is these overlapping wavefronts, as we'll see next week, that is a source of constructive interference where a lot of energy is being produced and released.
So when we ask the question, when is a shock wave formed? Okay, well, when you take a look at the simulation here, and you look at the wavefront diagram with these overlapping wavefronts, the shock wave occurs when the wave source outruns the wave it produces. In other words, when the wave source is traveling faster than the speed of the wave in the medium itself. For the case of the airplane, okay, well, when the plane travels faster than the speed of sound in the medium, a sonic boom will be produced. When you look at the simulation, you see the two observers, observer 1 and observer 2. Okay, the wavefronts have to actually pass the observer, okay, before the sonic boom will be heard. So in terms of wave interference, what is happening when the shock wave is formed? Well, we haven't formally talked about this phenomena that we call wave interference yet, okay, but we will next week. Okay, at this point, suffice it to say that whenever you have wavefronts overlap one another, that represents the condition that we call constructive interference, which means that you produce a very large amplitude wave. Remember that the amplitude of a wave is a measure of the energy that the wave transports. So when a large number of wavefronts overlap, creating a very large amplitude wave, that wave has a lot of energy, and that is what we call a shock wave. Breaking the sound barrier. Okay, well, it turns out that extra thrust from the plane engines, okay, are required to break through the wavefronts that have piled up in front of the plane. Maybe this is a phenomenon that you've heard about. Okay, the result is that once the sound barrier is broken and supersonic speeds have been reached, the plane can travel much more efficiently by expending less total energy. A historical note, there was a plane, it was called the Concorde. It used to fly across the Atlantic Ocean at supersonic speeds. Flying on it was probably the most expensive plane ticket that you could purchase at the time, okay, but not because of the fuel that was consumed. Once the supersonic speed was reached, the air travel was exceedingly efficient, and I should say exceedingly fast, and that's why, okay, the flight across the Atlantic Ocean at a supersonic speed, you could get from the United States to Europe very, very quickly. Of course, sonic booms are considered a source of noise pollution. So typically, supersonic travel is not allowed in areas where people live because it's not only unpleasant, okay, but it can be quite damaging to windows and to eardrums. Okay, so the sonic boom observed on the ground when the conical shock wave passes the observer, okay, you can see the conical shock wave illustrated here. And I just want to point out here, when you take a look at the illustration, you will notice that there are really two sonic booms in close succession to one another. Okay, one of the booms is heard when the front shock wave passes the observer, while the second boom is detected when the tail shock wave passes the observer. So when you consider the three observers in the diagram in the simulation, you see that for the observer on the left, both booms have been heard, okay, when the snapshot was taken here, as the conical shock wave from the front and back of the plane has passed, okay, the observer. Notice for the observer in the middle, however, that only one boom has been heard from the front of the plane, okay, while for the observer on the right, no sonic boom has yet been heard as the shock wave cone of interference has not yet reached that person's point in space.